Hello physics students. Today we're going to learn how to find the electric field of a charged straight bar. So I have here a piece of plastic. It has an equal number of protons as it does electrons, and that's why it's neutral. So suppose I rub it with something, another object, and I disturb that balance. So now maybe I strip electrons off or put them on. Let's suppose I strip them off and leave this charge positive, this bar positively charged in a uniform density. In other words, the charge is no more concentrated anywhere along this bar than anywhere else. So I want to find first the electric field at this midpoint. So that's what I have sketched here. Charge bar 1, determine the electric field at that midpoint. I get this little dotted line here as an axis for reference right here at point P. So take a moment to jot this down. Okay, so we don't know the formula, so we have to derive it. And as we did with the arc and the ring, there's a certain procedure we use to determine that electric field formula. You need to know that. And basically you need to know the big picture steps of every charge distribution. What do we do in step 1, 2, 3? Let me pause the video and see if you could remember the big major steps we take in solving such a problem. Okay, we can't use kq over r squared for the entire bar. kq over r squared, the only formula we have for electric field at this point, only works for a dot of charge, a proton or electron or a similarly shaped object. So I can use that formula as long as I slice this object into a small piece so that it acts and looks pretty much like a proton. So what I do is I just take some arbitrary part of the bar and I imagine in my mind, just with my imagination, slicing out a little piece that's length dx. Okay, so this is going to be our x-axis here. And the charge in that bar, knowing that this is the charge density, the coulombs per meter, the charge dq will be the coulombs per meter times the meter length of that bar. Coulomb per meter times meter gives me coulombs packed into that little dot. Now, if this bar is positively charged, that creates an electric field that points directly away like this. dE, like a little bit of electric field, okay? And I could calculate that, as I said, using kq over r squared, because this looks like a little tiny proton. Then, once I get the length of that arrow, so that's step 1, I cut this up and imagine dE, then I calculate what dE is using kq over r squared. Then I know it's a vector, and that when I sum up all the dE's throughout, caused by every little piece of this bar, eventually I'll get somewhere here in my summation, and and this piece over here will produce an electric field like this, with the same horizontal component as this dE, thereby canceling it. So whatever point I'm dealing with, there's some point mirror to the y-axis here, over here that cancels the x component. And so that means the only component that survives when we add up the electric fields of all these pieces is the y component, okay? Or actually I called it the z. All right, that's fine, the z. So that's what we state here. The z component here is this hypotenuse times the cosine of this angle theta, okay? So dE cos theta. Now what I'm going to do is fill in the pieces. So maybe what I'll do before I talk about it, I'll just pause and let you copy this down so you could listen. Okay, so again, I use kq over r squared because this is now looking like a proton because it's so small. kq over r squared. Where did I get that r squared, that term in the denominator there? Well, let's see. Oh, here we go. Well, r is how far away the charge is from the point it's creating the electric field. And so it's right here. We can find that by using the Pythagorean theorem. This is x if we define the middle as x equals 0. So this is x squared plus d squared equals r squared. Okay? Now, the cosine, I can replace that by realizing that right here, I've got a triangle. And I'll draw it a little smaller so it doesn't clutter up my diagram. D, x, theta, theta, so theta's right there. And this is the square root of these two squared. And so cosine is the adjacent side over the hypotenuse. Adjacent over hypotenuse, okay? Again, that's the z component of only this little piece. We want the z component of all the pieces added together. And when you add up little bits of something, infinite number of them, what you're doing is integrating, okay? So we integrate over the whole bar. So what does that make the limits? Well, if this is x equals 0, this is to the left half the length of the bar, minus L over 2. And then we add up until we get to halfway the length of the bar in the positive direction. So there's the other limit. What I've done is I've sort of brought together all the constants here. The K, Q, D, right? D doesn't change. Neither does the length of the bar, okay? The variables are the dx and this, which combine to the 3/2 power. Now, this actually turns out to be an integral that you can't you can't really do very easily with use substitutions or anything like that. So I just tell students, you just have to memorize this one, okay? That this dx over this to the 3, see what we're missing here is an x up here to be able to use a use substitution in our integration. Because up here, this is not the derivative of what's inside, so it doesn't work with a simple use substitution. You just have to remember, x on the top, d squared on the bottom, and the power to the 1/2. I forgot my limits, so let's add those in. Minus L over 2 to L over 2. Okay, so now it's time to plug in our limits and evaluate. All right, so K, Q, D, oh wait, you know what? We could also do this, get rid of that. So K, Q, L, D on the bottom. And then plugging in L over 2 in here and here gives me L over 2. Now when I do L over 2 squared, that gives me L squared over 4. Minus, now I'm going to plug in negative L over 2 here and there. So that gives me negative L over 2 up here. And then when I plug in negative L over 2 here and squared, I get L squared over 4. Plus d squared. Now notice we could do this, and L over 2 plus L over 2 gives us L, okay? So continuing on, K, Q, all this leads to L. And we could do this, okay? Now technically, I could rewrite this formula and be done, but sometimes it's customary to multiply the top and the bottom by 2. Again, you don't have to do this and you'll be 100% correct. But for some reason, sometimes people don't like this fraction within a fraction, within a denominator. So what you do now is when you distribute this 2 into the square root, you have to square it to bring it into a square root, right? So if you put 4 into a square root, that's like 2, right? So we square it and we distribute 4 to these two terms, giving us K, Q, d, the 4 goes away, okay, so there it is, the electric field. Now remember that I always say when you have a formula like this, it's good to do a unit check quickly if you have time. We know the electric field formula is K, Q coulombs over R squared. Do we have these units in this more complicated formula? We've got our K, and we've got our coulombs in the top. Good, okay? We've got a meter over here, and then meters squared to the 1/2 power is meters. And so we have K coulombs over meters squared. So again, the formula appears to be correct. And then we could also write that the X component of the electric field is 0. We know that just from our thinking all the way at the start of the problem. Okay? So, more difficult than the arc in the ring because of this integral here. But again, just a reminder, you know I want to drill this in. What you do is you slice this first into a little proton or electron and imagine the electric field it uses here or creates here from kq over r squared. You could calculate its magnitude. Then you imagine before you integrate, you imagine how you're going to integrate and which component goes away. And sometimes no component goes away, but in this case it does. The x component goes away, only the z component survives. So we use an appropriate trig function to pick the right component, and then we integrate. So it's like 3 big steps, really, okay? All right, so the other thing I want to do is sort of play with this formula a little bit. What if this bar was very long, okay? In other words, infinite in length. And before I go on, this is a theme that comes up a lot in this course. In math, infinity, you imagine it's something gigantic and it's bigger than we are by, like maybe bigger than our solar system. Oh, that's an infinite distance. But in reality, the concept of infinity is actually relative. Let me ask you this. Would you think of this as an infinite distance? You would say, of course not. That's like, maybe a millimeter or something. But if you do a ratio comparison to this compared to the size of an atom, which is what the world the electron is in, like its little solar system or its little planet Earth is the atom, right? This millimeter is proportionally the size of our solar system compared to us and planet Earth. So if I said, well, if I were to go beyond Pluto's orbit, is that kind of infinity? You say, yeah, that's really far. We could probably consider that kind of like almost an infinite distance away. To an electron, that's infinity away from an atom. So when I say an infinite bar, it could only be this long. But the key condition that must be true is that I am close enough to the center of the bar, so if I place something here and I look far away to either side of the bar, it looks like it's almost infinite. So it's really a relative thing comparing this distance to the length of the bar. If the length of the bar is much bigger, and we could play around and figure out exactly how many, like the ratio of how much longer it has to be, but it's not necessary. The point is, it just appears long enough where we could consider it infinite, and later in the course we'll talk about exactly what that means in quantifying that. So let's suppose we want to know what the electric field is if we could consider the length of this bar infinite, okay? And some of you might be saying, well, if we plug in an infinite number here in the denominator, it's going to make the electric field 0. Well, it is technically if we keep the charge constant. But what if we keep adding length to the bar and charge at the same time? In other words, we maintain the same lambda. So, So there's our formula, and we're going to see what happens as we let L elongate. And to help us to understand that, the first thing I'm going to do is multiply the top and the bottom by 1 over L. And what I'm going to do is combine this Q over L into lambda. So on the top, I have K lambda D, and then I'm going to bring this L under the radical, which makes it a 1, not a 1 over L, but a 1 over L squared dividing into these two terms. So L squared over L squared is 1. And then over here we've got 4D squared over L squared to the 1/2 power. Now what we're going to do is only now find the limit as L, the length of the bar, goes to infinity while we maintain the same charge density. And what you could see here is that this term, because it has L in the denominator, will gradually go to 0 the longer L gets. It's like dividing by a huge number. That goes away. So we have radical 1, which is just 1, and that gives us EZ there. Nice simple formula, okay? Uh-oh, I just realized I lost my 2 over here. Good thing I caught it, okay? So, remember my unit check doesn't catch that. Maybe I did that on purpose to make that point. No, I didn't. I really made a mistake. So, another thing, I just want to remind you that this is equivalent with K being equal to something called 1 over 4 pi epsilon 0. We could also write this as lambda over 2 pi epsilon 0. And the reason why I mention that is because look at how long it took us to find the electric field for an infinite bar. We had to break it up into pieces, integrate, simplify the formula, do this. Like 4 chalkboards I filled up. We're going to learn in the next unit called Gauss's law, a technique that'll get us this formula in 3 lines, okay? So what we're doing right now is finding the electric field the hard way. In the next unit, something called Gauss's law, it's going to be easier, okay? So something to look forward to. Well, we're not done. We're going to look at a couple more situations where we can find the electric field for a charge bar. So let's move on to charge bar 2, okay? Maybe I put point P over here. Okay, let's see, maybe, yeah, a little bit down here. So, and this is the same thing, a certain charge, length L, positive, so it's got the same lambda. And so basically what I have to do here is when I, again, follow this process of slicing this in my imagination into something that looks like a little proton, dq equals q over L dx. So then I imagine that makes a certain dE. And then I could find that with kq over r squared. Then I'm going to integrate over the length of the bar. But when I do that, I realize that in this case, none of the components cancel. In other words, as I'm going like this and adding up all the dE's, this dE points straight up, then these progressively point to the side, but never does any electric field point this way to cancel the horizontal component. So what I have to do now is, if I imagine theta here, I've got to find both the z component and the x component. So I could say that E in the z direction will be the integral over the bar, and maybe I could call this x equals 0 and that x equals L this time, of the dE vector that I get from kq over r squared. And to find the z component, I am using cosine again. So it's like the details that I already erased. I'd replace this with kq over r squared and this with cosine based on the triangle here with the dimensions, and integrate and solve. But once I get the z component, I'd have to do a whole nother calculation for the x component. And maybe it points left, so I'll put a minus sign. From 0 to L again, dE, which I find from kq over r squared, times the sine function now, because that's the opposite side, and this is the hypotenuse. Well, you'll be happy to know, or maybe not, maybe you'll be disappointed to know that I'm not going to work these out. Okay, I just showing you the big idea in case the AP asks about it, which I doubt, you know. They probably would not do that, but you never know. So I mentioned that you use cosine and sine to find the two components. One more example, charge bar 3, okay? So I'll pause to give you a chance to jot that down. Okay, let's continue with charge bar 3. Okay. I got the bar, Q, L, oops. Got a certain charge. Doesn't matter if it's positive or negative. All that'll do is change the direction of the arrow. But now my point P is over here. So we did here, we did it on the, up here. Now we're doing straight along this axis, a point right there. We want to find the net electric field caused by this bar. We follow the same process. We use kq over r squared, which is okay as long as we imagine slicing this into something that looks like a proton or an electron. This will be a length dx, a charge dq, equaling lambda, the coulombs per meter, times the meter, gives me the coulombs in that little piece. That creates an electric field if this bar is positive, pointing directly away. And there's my dE. So I could find that but before I go into the details, what I do is think a little bit ahead and say, okay, I know I'm going to integrate this, which means I'm going to add up all the dEs of all the pieces. So, do I need to find a component? Is there part of the electric field that'll cancel when I do this integration? And the answer is no. Every piece along here always creates an electric field pointing to the right. So I don't need a trig function this time. What I could do is just say that dEx, oh wait, let's do color coordinated, dEx will be K, Q, over, what I'm going to do is call this distance x. Okay? So that makes it easy to just call this x squared to make the integration easier. Okay? So once again, as I said, I'm going to integrate, add up all the pieces. So I'm integrating that function. No need for trig function. So pause the video to give you a chance to jot that down. Okay, let's move on. So now, if we add up all the pieces, we will have the total E in the x direction. We're going to add up, leave some space for the limits. I'm just going to rewrite this as K, Q over L, all the constants, x to the minus 2 dx. All right, so the limits, okay? So if this is x, what does x have to change from what value to what value for me to sweep across the bar as I'm integrating? Ah, I forgot. This is some distance d from the front of the bar. So what I need to do is I need to not start at 0 because then I'd be integrating and there's no charge here. X, the bar begins when I get to x equals d. And then I integrate from starting at d and I end at d plus L. So there are my limits from d to d plus L. Okay? So continuing on, K, Q over L. Add 1 to the exponent and then divide. Now what I'm going to do is plug in my limits. One over d plus L minus 1 over d. So actually, let's leave a little space here. So what I'm going to do is distribute this minus sign first. Then what I'm going to do is find a common denominator over here to simplify. D times d, d over d. And then over here, d plus L, d plus L. And so what I have is d plus L minus d in the top, which just gives me L. The L's go away, and I get my final result. Okay. So let me pause and give you a chance to jot that down. Okay, so I just want to say one thing about that formula. Well, a couple things. We could do a unit check, okay? We have K coulombs over meters squared, so that's good. The other thing we could say is imagine that we're very far from the end of that bar. Maybe I shouldn't have erased it, but so we got the bar like this, and we're way out over here, somewhere far away, so that D is much, much bigger than the length of the bar. What you could see, if we get far enough from that bar, that this L becomes insignificant when we add, like, say, this is 100 meters and that's like 0.1, right? That's like insignificant. What we have is KQ over D squared, which is the electric field as if the whole bar were actually now a proton. So again, you get far enough away from a little bar like this and you start looking at, oh, it looks like a little dot of charge. No, it's a bar, but from far away, it acts like a proton, okay? So that is the electric field of a charged bar. A little more challenging than the arc and the ring, but the same process. You use KQ over R squared by slicing away a little piece of this so it looks like a proton, or a ring, you slice a little, or a bar, you slice a little bit. You imagine that DE vector. Then you imagine as you're adding up, is there a component that cancels? If yes, then you have to select out the right component with the trig function, sine or cosine. And then you integrate, okay? So that's the general process for finding the electric field when it's spread out using KQ over R squared. All right, I'll see you in the next physics video.